matrix is the arrangement of numbers, and it's a special arrangement of numbers. For example, if you have numbers 1, 2, 3, 4, 5, 6, it can be arranged as 1, 2, 3, 4, 5, 6, or it could be arranged 1, 2, 3, 4, 5, 6. These are different arrangements, and if you notice, it looks like some sort of a rectangle. So if you have a matrix or an arrangement of number, the plural is matrices. So it has 3 rows. So the 3 rows that we have, 1, 2, 3, and it has 2 columns, and the columns are 1, 2, and here it has 2 rows, 1, 2, and it has 3 columns, 1, 2, 3. The size of a matrix is written as, first we write the row, so 3 here by 2 here. So we say it's a 3 by 2 matrix. And here we have 2 row times 3 columns. That's it. So when we have a matrix, it's all about the arrangement, and the arrangement is mentioned that it is a number of rows with the number of columns. So let me write it here. So the size of a matrix is row by column, and it is written as a number times another number. We don't multiply it, we just call it times. When we have these matrices, it is possible to have a square matrix. A square matrix is simply where the number of rows and the number of columns are equal. So this can be 1, 2, 3, 4. So here we have 2 rows and we have 2 columns. So this is a 2 by 2 square matrix. The important thing about matrix is the operations, the arithmetic operations. So the arithmetic operations are addition and subtraction. So it's fairly simple. Let me show you how this is done. Addition is, let's write down the matrix 1, 2, 3, 4 plus we have another matrix 5, 6, 7, 8. So both are 2 by 2 matrices. It is important that the sizes of the matrix, they're same. So addition is fairly simple. We just add up the same positions. 1 plus 5 is 6. 2 plus 6 is 8. 3 plus 7 is 10. 4 plus 8 is 12. That's it. That's all there is to it. Subtraction works in a similar way. So when we have subtraction, 1, 2, 3, 4 minus 5, 6, 7, 8. So the subtraction works. You just subtract the individual positions. 1 minus 5 is minus 4. 2 minus 6 is minus 4. 3, turns out everything is minus 4 here. 3 minus 7 is minus 4. And 4 minus 8 is minus 4. Subtraction. So the individual positions are like that. Another idea is scalar product. Scalar product. Scalar product is multiplying the matrix with a single number. So if you want to multiply a matrix with 3, 1, 2, 3, 4, you want to multiply this matrix with a scalar product, it has to be 3 into 1, 3, 3 into 2, 6, 3 into 3, 9, 3 into 4, 12. So this is the scalar product. It doesn't matter, in case of scalar products, it doesn't really matter what the size of the matrix is. If I want to multiply 2 with 1, 2, 3, 4, 5, 6. So this is a 3 by 2 matrix, 3 rows and 2 columns. Then it would turn out to be 2 into 1 is 2, 2 into 2 is 4, 2 into 3 is 6, 2 times 4 is 8, 2 times 5 is 10, 2 times 6 is 12. So that is the scalar product. Now A more challenging arithmetic operation apart from addition and subtraction, which is fairly simple, it's the multiplication of matrices, which is not as straightforward as it might seem what addition and subtraction is. So this is what it is. So if you want to multiply two matrices, multiplying matrices. So if you have 1, 2, 3, 4 and you want to multiply this with 5, 6, 7, 8, so this is what is done. First, the row is taken here. So this row is taken, and with this we multiply this column. The first reaction might be, since we add the same position, 1 plus 5, 2 plus 6, 3 plus 7, 4 plus 8, this is not what's happening. This is a bit different. It's more complicated. So the obvious thing might be it should be 1 into 5, 2 into 6, 3 into 7, 4 into 8, but this is not what's happening. So what is happening? The first row is taken and it is multiplied with the first column of the second matrix. So when this is done, we get something like 1 times 5 is going to give us 5 plus 2 times 7 is going to give us 14. So what we are doing here, we are multiplying this 1 with this. So this is the product. And then we are multiplying this 2 with this 7. So this is the product. So this is what we are doing. So the next thing that we have to do after that is then we multiply this same row with the next column. Then it turns out to be 1 times 6 is 6 plus 2 times 8 is 16. And we proceed to the next one. So the next row here is 3, 4. So when we do this, it becomes 3 times 5 is 15 plus 4 times 7 is 28. Then we move on to the next column, which is 3 times 6 is 18 plus 4 times 8 is 32, and we simply add it. So 5 plus 14 is 19, 6 plus 16 is 22, 15 plus 28 is 43, and 18 plus 32 is 41. So that's the addition. This should be 50. This should be 50. So 4 plus, yes. So that's the addition, and we add it, and that is the multiplication of two matrices. Now the multiplication of two matrices doesn't mean it has to be of the same size only. It can be of different, because every multiplication is not allowed. What happens here really is the first of this is, suppose this is the size of the first matrix, and the size of the second matrix is this, B times C. You can multiply two matrices only if this thing and this thing matches. That means these are the possible multiplications that are allowed. 2 times 3, 3 times 1, or 3 times 1, 1 times 2. So it doesn't really matter what the others are, but this and this, they have to match. So if you take a look at, if I give you two examples, the first one is 2 times 3. So 2 rows, 3 columns. So 1, 2, 3, 4, 5, 6 multiplied by, we often don't write this multiplication simple. We just write this bracket. This would be 3 rows, 1 column. So let me write 7, 8, 9. So it has 3 rows and 1 column. This multiplication is of course allowed because this column of the first matrix matches with the number of rows of the second matrix. So that makes it. So we are going to multiply this row one more time with this column over here. So we have to do this multiplication. So let's move on with this. So 1 times 7 is 7 plus 2 times 8 is 16 plus 3 times 9 is 27. Next we have the next row over here, which is 4, 5, 6, and when we multiply that we get 4 times 7 is 28 plus 5 times 8 is 40 plus 6 times 9 is 54. Yes. So this is what we get. If we add this, now I'm going to use a calculator now. We are going to get 7 plus 16 plus 27. This is 50, and 28 plus 40 is 68 plus 54. This is going to be 122. Now if you notice, this is 2 by 1 and the size of this matrix is 2 rows and 1 column, 2 by 1. That means we can safely say that whatever is left over, that is the size of the remaining matrix, 2 by 1. So the size of this matrix is going to be 3 by 2. So let's do another example with this type of sum. If we have a 3 by 1 matrix, that is going to be 3 row 1 column. So 1, 2, 3, 3 row 1 column, and we have 1 by 2. So 1 row 2 columns. So 4, 5. So can we multiply this? Of course, because this thing and this thing matches. So it is allowed that we can multiply this. And the product is going to be 3 rows. That means 1, 2, 3, and 2 columns, 1, 2. So that is going to be the product. So let's check whether this is the case indeed or not. So 1 times 4 is 4. The next one. So this is the first row. The first row contains only one element, and this is the first column. We multiplied that, and this is the second column. That's what's happening. So that turns out to be 1 times 5 is 5. So we got our 2 columns now. Now the second row. So 2. So 2 is going to be 2 multiplied by 4 is 8. So we get 8 here. And 2 multiplied by 5 is 10. Now we have the third row to think about. So this is the third row. And it turns out to be 3 times 4 is 12, and 3 times 5 is 15. So we have a product which is 3 rows and 2 columns. There's a special bunch of matrices known as 2 by 2 matrices. So 2 by 2 matrices. 2 by 2 matrices, which is the plural of matrix. So if it's 2 by 2, that means the number of row equals the number of columns. That's a square matrix. So 2 by 2 matrix is a square matrix here. So the first thing that we have to know is the determinant of a 2 by 2 matrix. The determinant of a 2 by 2 matrix is a special number. So the determinant is a special number with which we can use other stuff. We can solve systems of linear equations and things like that. So if you have a 2 by 2 matrix like this, I'm writing the algebraic version A, B, C, D, and if you want to find the determinant of that, you just simply write it with vertical bars over here. You write A, B, C, D. So this is a matrix, an arrangement of numbers, and this is this 2 bar signs over here means you're finding the determinant of that matrix, and that determinant is a special number which we multiply this A with D. So we multiply this A with D, and we multiply this B with C, and we subtract the 2. That's all we do. So it is going to be AD minus BC. That's the determinant of a matrix. So let me write here, if you have a matrix 1, 3, 4, 5, and they ask for this bar thing here. So you want to find the determinant of that matrix. That would be 1 times 5 is 5, minus 4 times 3 is 12, and the determinant is minus 7. That's what we get. Now, if the determinant of a matrix is 0, this can happen if each and every term is same, or it can also happen in other situations. If you have a matrix like this, 1, 1, 1, 1. So what happens? The determinant becomes 0 because 1 times 1 is 1 minus 1 times 1 is 1. 1 minus 1 is 0. And it doesn't mean that all the elements has to be the same. It could be also different. For example, if you have a matrix 2, 6, 1, 3, we know that the determinant is again going to be 0 because 2 times 3 is 6, 6 times 1 is also 6. There can be many different types of a 2 by 2 matrices where the determinant is 0. Whenever a determinant is 0, we call that matrix a singular matrix. So we call that a singular matrix. Remember, first of all, it has to be a 2 by 2 matrix for it to be a singular matrix. And if it's not a 2 by 2 matrix, you cannot find the determinant. So the special rule is the 2 by 2 matrix here. The next thing that we have to find out is the inverse of a matrix. Inverse of a matrix. Now, you cannot invert every single matrix. It is important to remember singular matrices has no inverse. So you can only inverse non-singular matrices. Non-singular matrices. Okay, so this is how it works. So if you want to find the inverse of a matrix, suppose you have A, B, C, D, and you want to find the inverse, and the symbol here is you put a little minus 1 over here. That means the inverse of a matrix. In determinant, we put 2 bars, and inverse of a matrix, we put a little minus 1 over here. So the rule is this. You take the reciprocal of the determinant, AD minus BC. Now that you see if it is 0, we cannot divide a number with 0 that is undefined. It's a huge number. So that's why if it's 0, if it's a singular matrix, we cannot have the inverse of that matrix. And the rest is just a trick. You change the positions of these diagonal. You put the D over here and the A over here. And then you change the signs, plus minus signs of these. So these are both positive. You make it minus B and you make it minus C. So that's how you find the inverse of a matrix. So an example would be, suppose we have a matrix A which is 1, 2, 3, 4, and you want to find the inverse of this matrix. So this is going to be 1 divided by 4 ones are 4 minus 3 to the 6, and then we can just change the position here. So this is going to be 4 over here, this is going to be 1 over here, and this is going to be minus 2, and this is going to be minus 3. You can keep it like this, or you can do the scalar multiplication. Remember, this is a constant 1 by minus 2, so minus half. So if I write here minus half and multiply it with that, okay, so that would mean I'm going to multiply minus half with 4, then minus half with minus 2, then minus half with minus 3, and minus half with 1. So this is what it looks like. Okay, so what we have here is minus half with 4 is minus 2, minus half with minus 2 is 1, minus half with minus 3 is 3 by 2, and minus half with 1 is minus half. So that's an inverse of a matrix. There's a special rule worth remembering. If you multiply the inverse of a matrix with itself, you end up with a special 2 by 2 matrix called the identity matrix. An identity matrix is a matrix with ones and zeros. So this particular identity matrix is the diagonals are 1. So that's the special case. When you have the inverse of a matrix multiplied by the matrix itself, you have a special matrix. It's called an identity matrix. It's a particularly a 2 by 2 matrix in this case, with diagonals as 1s and the rest as zeros.